Women Wednesday today. Joining us, we have Matt Sellin, of course, one of our typical wise guys who joins us. We also have a special guest, Professor Nadia Mason. Good morning, guys.
Good morning.
Lady, women. So excited that you're joining us. Matt, first of all, tell us a little about Nadia and why you brought her with you.
Right, so I realized I've been doing this for almost 15 years, and why should I have all the fun when we have these brilliant young scientists at the university, especially in the Department of Physics that I'm familiar with, and Nadia is amazing, so I thought, she can help me out, because I'm getting old and tired too. So I just need some help. And so she's going to be coming in and helping out a lot, I hope. And so I just want to introduce Nadia Mason, and you can say a little about yourself, or you guys can ask questions before we start.
Well,
what do you want to do?
Yeah, real quickly, tell us how you kind of got into science and what gets you excited.
Oh boy, well, I was interested in math. Physics engages me. I like thinking about the way the world works. It tells you the fundamental way the world works, from the sky is blue to why we have transistors. And so you can learn everything through physics, fundamental.
I love that.
Right, so everyone wants to know everything. So what engages me? These days, I spend most of my time thinking about physics, thinking about the way the world works, and also raising my two girls. So shout out to Marlo and Hazel in the green.
That's awesome.
All right, what do you got for us today?
Okay, so I study the physics of materials, which means that I think about what interesting behaviors materials can have and what new properties they can have that are interesting, and also that lead to new devices, new sorts of electronic devices. So I think of us as the people who brought you the transistor. So I think about something, for example, called superconductivity. This is an example of a superconductor. It's just a metal, kind of a brittle metal, yttrium, barium, copper oxide. And just to give you an example of the sort of cool properties you can get from interesting materials like this, I can take, here's that same superconductor. Oh gosh, okay. That is another interesting property of material. You can put it inside just a little packet like this, and now I'm going to put it on top of a magnet over here. So I put the superconductor on top of a magnet, and it floats.
Oh.
And you can see that it's just floating above there, right? There's nothing underneath it. So I'll tell you next week how that works. But this just shows you, if you have interesting materials, you get these really cool behaviors. And I can show you one more thing that it does. Let's take this off here. We're going to give another little dunk in the nitrogen. Put it down there.
And what are you dunking it in?
In liquid nitrogen. So the reason you don't see this in every day is it has to be pretty cold to get this to work. But the cool thing about this material is that it has zero electrical resistance. And so let's not do that. Oops. Okay, this is a little finicky. But watch this. So it has no electrical resistance. Imagine this as a train that's floating, right? That doesn't lose power, right? The implications for power and energy are enormous, and it's just kind of amazing. So
I feel like I'm mesmerized.
Yeah, exactly.
And so as we say, it's not magic, it's physics.
Right.
This is the physical property of that metal inside there. When it gets cold, the electrons work together in such a way that they have no resistance, they push away the magnetic field, and it can just float above magnets.
So that's just magnets that is floating around?
It's floating around magnets, yeah. And there's no other trick there, just the metal will float around magnets.
That's so cool.
And then we slowing down. And what's happening here? Is it the nitrogen's kind of wearing on? What's happening?
Yeah, it's getting a little bit warmer. So as it gets warmer, it doesn't float as well. It stops becoming superconducting once it gets to room temperature.
Okay.
So,
how long do you typically have to let it sit in nitrogen before it can get, or what temperature do you have to bring that to for it to actually work like that?
So this material can work at about 100 Kelvin, which is 150 degrees below zero. But nitrogen's 77, so in nitrogen it works great. Room temperature, we're working on getting it to work at room temperature, and then you can just imagine having this in a car.
I was going to say the practical applications that you have from this are just amazing.
Right.
So tell us a little bit more about, kind of some of the things that you're hoping to show us through these segments.
So, like I said, I focus on the physics of materials, so I'd like to show you a lot more of the interesting things we can do with materials. I think that we all are so accustomed to having things like our iPhones and our smartwatches, and we just take that technology for advantage. And so one of my aims is to show you how we go from the physics of materials to creating things like transistors and then iPhones, and what new technologies may come about in the future from the new things we're studying.
I love it.
I'm ready. And next week, you're going to tell us why that happened, right?
Yes.
I like it.
I'm gonna try.
Nadia, thanks so much for joining us. Matt, thanks for being back with us today. We appreciate it. We've got more of the morning show coming up next. Before we go, though, we want to remind you, send in those questions if you have it for our wise guy or wise women here on the morning show. You can do that on Facebook Ask away. We'll be right back.